Welcome to ScaleUp University. Welcome to the course on building applications with AI agents. So this is the lecture 3 of module 1. So in this lecture, we will discuss agents versus traditional machine learning systems. So we'll analyze the difference between AI agents and traditional machine learning systems. So there is like a very big misconception that agents are just machine learning models with extra steps. And actually, that is wrong. Agent is like a very different, like AI agents, they are very different from traditional machine learning models. So we cannot say that AI agents are just the extension of machine learning models. That's a very big misconception. And all that we will clear. So in this lecture. So the idea is that if you talk about traditional machine learning systems, they are designed to recognize patterns and predict labels. So machine learning systems, they are very good in recognizing patterns and they can just predict labels. They can do the predictions. Predictions like they can either do classification or regression or recommendation or forecasting. Now the limitation of traditional machine learning systems is that they are very passive in nature, meaning to say that they can only do the prediction. They cannot plan, they cannot reason, they cannot act. So they are passive, they are isolated and stateless. Isolated means like the idea is that machine learning system, machine learning model is like very specific. Like it is not general purpose. You can achieve only one objective. So it's isolated and it's very specialized and it is stateless, meaning to say that inputs it does not remember, it does not remember the interaction. Like when you're interacting with a machine learning system, that interaction it will not remember. Every input is a new input regardless of the previous state. And because of like these are some very important limitations of machine learning systems, and they lack context, they are not at all adaptable, they're like very brittle in nature, and they lack agency, they cannot act. And interestingly, AI agents, they are very different from traditional machine learning systems. And that is what this lecture is about. The crux of this lecture is to discuss the difference, like how AI agents are different from traditional machine learning systems and how they are very much powerful. That we will discuss. So now you are getting some overview about okay, what is traditional ML systems and how AI agents are very much different from traditional AI systems. So AI agents, we can call it as the architectural shift. It's like AI agents is not like a minor upgrade. It's not minor upgrade of machine learning systems. Rather, it is a total like architectural shift wherein agents acts like a full decision systems. So they keep on taking inputs from the environment, from the real world, that is a perception and sensor. And agent have state, they can reason and plan, and they are aligned with a goal, and they perform some actions which affect the real world, and they keep on reiterating their strategies, that is the reflect and adapt. So this framework of AI agents, it is very much different. It's an architectural shift from machine learning systems, and hence now we are convinced that AI agents are different and much more powerful than traditional machine learning systems. And that is what, in some good detail, we will discuss in this lecture. So, this lecture establishes how AI agents extend ML. So, AI agents, they integrate perception, reasoning, and action, which was missing in traditional machine learning systems. Machine learning systems are not at all concerned with any goal or objective, but AI agents, like for machine learning systems, there is an objective to minimize the loss, minimize the error, but they don't have any specific goal. But all AI agents, they are driven by goal. They are autonomous in nature and they are goal directed decision making. They are adaptive, robust, and they continuously learn and evolve because based on the input and the goal, they make some plan, they act on it, and they reflect, they assess the outcome, and based on that, they adapt their strategy, they re-strategize. So they keep on evolving, they keep on continuously, they keep on learning, and until they reach the goal. And this is very much different from traditional machine learning systems. And that is what this lecture will be about. So if we look at the topics we will be covering in this lecture, so we will be discussing what traditional machine learning systems are designed for, task specific nature of machine learning models, training time versus runtime behavior, static inference versus dynamic action, lack of planning in classical machine learning models, boundaries and brittleness of machine learning systems, how agents extend machine learning systems, planning plus execution layers on top of machine learning, real time adaptation, decision loops versus one shot prediction, why agents are not just LLM wrappers. And finally, we will conclude this lecture by discussing side by side comparison summary. So all these topics we will discuss one by one in this lecture. So this is the module 1, introduction to agents, lecture 3, agents versus traditional machine learning systems. And this is the first topic we are going to start, that is what traditional machine learning systems are designed for. So if we talk about traditional machine learning systems, so at their core, they are very good in pattern recognition. So we can call it like they are statistical function approximators. So machine learning models, machine learning systems, they act like statistical function approximators. So the idea is that they make use of statistics, means lots of observations like samples, and they start with a guess, and with the input and output, they start to minimize the losses. So the idea is that they start with a random guess, so some weights, and then for the input they do the prediction, and they know the real output, and the difference is the loss. And based on the difference, the machine learning systems, they optimize, they know that okay, how to update the weights, and they keep on updating the weights to minimize the losses, and they keep on doing it until the loss is minimized. And once that is done, any new input you give to the machine learning system, it will give like a approximate, like a very close real prediction. And that is how it works. So basically machine learning systems, probability and statistics plays a very important role. They are statistical function approximators. So what they do is that they map input and output. So while training the machine learning model, we know the input, we know the output. So if we have like thousands and tens of thousands of samples wherein input and output we know, so machine learning model, it will devise the mapping function. It will identify, it will uncover the mapping function, because the mapping function is the logic, is the way to solve the problem. See, until now, in traditional programming, what we have been doing is that we have to solve a problem. So we write an algorithm for that, wherein humans, they used to code every step. The function map, the function we used to write, and we used to give the input, and we used to get the output. So that is what the traditional software engineering was, wherein humans were the one, human intelligence was involved in solving a problem. Okay, we know that okay, we have to sort numbers. For a basic example I am taking, so we used to write the algorithm for that. Okay, to sort the number, these techniques we should apply. But interestingly, in machine learning, since it is artificial intelligence, uh, the algorithm itself will learn to solve the problem. So here we just have to provide, as humans, the role of humans will be to just provide input and output, the data, training data, and machine learning model on its own, it will devise the way, it will devise the mapping function. And that is something which makes it artificial intelligence, because here the problem is solved the function is written by the algorithm itself, by the machine learning system itself. If we talk about the primary objectives, like typical objectives of machine learning systems, so they can predict a label, that is like classification. Classification means, okay, input is there, we can classify it, we can assign a category, like, okay, this image, it is of a cat or a dog. It Machine learning systems, they can estimate a value, that is regression. Regression means it can predict a value, it can predict a real number, like price. It can rank items, that is recommendation. Machine learning systems, they can recommend, they can rank items, they can order results, and they can detect patterns. They can identify structures, anomalies, and they can also do like time series forecasting. All that they can do. So if we look at the examples, like we have image classification, spam detection, price prediction, recommendation systems. So all these things, like you might definitely have come across image classifiers, spam detectors, like the Gmail, all the mail, they have spam detectors in it, price predictions, recommendation systems. We can build all this using traditional machine learning systems. So traditional machine learning systems, they are excellent at pattern recognition. They can recognize patterns. They're excellent at generalization within a specific task, within a fixed task. Like they can only perform a fixed task, a specific task. Because if you have a machine learning system for image classification, it can only classify the image, and that too, whatever you have trained it to do. So machine learning systems are very much specialized. They are not general purpose. You cannot use it to solve many problems. They're highly specialized. So they are generalized within a fixed task, and they operate inside known data distributions. So this is like a very good thing about machine learning systems. Like whatever patterns you teach it, it will sincerely learn it, and it will be very good in learning those patterns. And any input you give it which has those related patterns, it will very easily identify it and give you the right answers. So machine learning systems are excellent at pattern recognition, and they can operate inside known data distributions. Okay, now we will look at the task specific nature of machine learning models. So as we already saw, when we talk about machine learning systems, like the core constraint is like they are trained for one specific task. Like one machine learning model is good in solving one particular problem. So they are trained for one specific task, and they operate within a fixed problem definition. Like whatever patterns you will teach it, it is applicable for that only. If any input you give it which is way away from that pattern, then it will start giving wrong answers. So machine learning systems, they are trained for one specific task. They operate within a fixed problem definition, and they assume the task will not change, which is actually not applicable also, because the real world is very uncertain. So machine learning models, it it assumes that, okay, these are the patterns and these patterns will be forever, but it does not happen. For example, if we talk about COVID-19, COVID-19 was a very big shift, the pandemic. It was a reset. So before pre pandemic era, whatever the patterns were, after COVID-19, most of the patterns they changed. So the machine learning models trained before COVID-19, they became obsolete. They became useless after COVID-19, after pandemic, post pandemic. They started giving wrong answers because the patterns they got changed. And that's a very big constraint. So now we are getting a feel of traditional machine learning systems, machine learning models. They are task specific. They're trained for a specific task. They operate within a fixed problem definition, and they assume that task will not change. But that is not true. So machine learning systems, models, they cannot adapt with time. They cannot automatically adapt. Whatever we have trained, it has got some learning, Now it can answer based on that knowledge. So in machine learning systems, we train the system, so we impart some knowledge. Now that knowledge can become absolute because we are evolving. So machine learning systems cannot adapt over time. So let us look at one example to get more clear understanding. So I have an input text and I have a sentiment classifier. Now this sentiment classifier, what it does is that it will analyze the text and it will classify whether that text is like a positive, neutral, or negative. Now this sentiment classifier, when we trained it, it's a fixed model because it has got some patterns, it has learned some patterns, and the knowledge is fixed. So it always classifies sentiment. So based on the input text, it will always classify the sentiment. Like it will tell whether the input text is a positive or negative. So the output label will be positive or negative. Now this sentiment classifier, it can only do the prediction. It cannot act on the results. It cannot decide what to do with the result, and it cannot add new knowledge, or it cannot redefine its objective. No self correction. So the key limitation of machine learning models, it's very much clear that machine learning models do what they are trained to do, nothing more. So whatever you train them to do, they will do that. They lack agency and adaptability. Like they cannot act on their own and they cannot adapt. The knowledge is fixed. So this is very, very clear that okay, machine learning models, they are task specific. Whatever training you give the patterns they learn, they can do that. They can do the predictions in that fixed domain, nothing more. They cannot adapt. Their knowledge cannot evolve over time, and they cannot act. So they lack agency and adaptability. Training time versus runtime behavior. So in traditional machine learning model, they are the frozen model. Frozen model, why we are telling that? Because see, intelligence is baked in the at the training time. So while training, whatever patterns it will recognize, it will learn only that. So the intelligence is baked at the training time, and that is fixed. At runtime, model only performs inference, because you see what we are discussing the training time behavior versus runtime behavior. For traditional machine learning systems, in the training time, the intelligence is baked because the pattern learning and all the intelligence is baked at the training time. And runtime, model will only do the inference. Okay, this is the input, it will do the prediction for that input. In the runtime, there is no scope of learning, and it cannot reiterate or change the strategy. All that it cannot do. So we say that for traditional machine learning systems, it is the static pipeline wherein we train the model. So we bake the intelligence and then we deploy the model. And once the model is in the production, it will just do the prediction. That's it. In the production, the model cannot learn and it cannot adapt and it cannot act. It will just do the prediction. And hence we are calling it like the static pipelines. Why it's static pipeline? Once the pipeline is made, it can run. No need for human intervention. Like training is a one time process, deployment is a one time process, and once the model is there in the production, it will just take the input, and based on its intelligence it will give the output. That's it. And hence traditional machine learning systems are frozen model. But if we talk about AI agents, they are the live decision systems. So they are very dynamic in nature. So here, intelligence is partially learned, partially constructed at runtime. So very important. See, in AI agents, the idea is that the intelligence is partially learned and partially constructed at runtime. So the idea is that at during the training time, partial intelligence is learned, but runtime also learning happens. So at runtime for AI agents, it will not just do the predictions, rather it will decide actions based on the inputs. It will interpret the intent and it will decide actions. It will plan. It will make an action plan. Then it will choose tools to perform those actions. It will act, it will execute those actions, and it will reflect, it will assess the outcomes, and based on that, it will revise plans. It will learn from feedback, it will revise plans, and it will keep on doing it. So AI agent is something wherein if you give the input, it will keep on running the loop, the learning loop. It will keep on running until the goal is achieved. Until the goal is achieved. So hence, for AI agents, it is a dynamic loop pipeline wherein AI agents, they constantly like keep on observing perception. They observe, then they decide, they make the action plan, then they act on it, then they reflect, like they learn from the outcomes, and they revise the plans, that is the adapt. And then once again they will observe, and they will keep on doing it until the goal is achieved. And hence we are calling AI agents as the live decision system. So now I hope it's very clear that traditional machine learning systems are like very passive, wherein one time effort you put, the model is live, model is live, and like it can do a specific task of prediction, that's it. But for AI agents, it is a live decision system wherein it will keep on running until the goal is achieved. So it's a dynamic loop pipeline. So AI systems, AI agents, it's a live decision system, not a frozen model. And machine learning systems are frozen model. Static inference versus dynamic action. So see, machine learning systems, they are like static inference. Now we already saw that, okay, we have a machine learning model. Now that machine learning model, we trained it. Like when we trained, we baked the intelligence. The learning happened. It acquired some knowledge during the training time. Now that machine learning model is stateless. It has no memory, no persistence. So it's very important. Machine learning model, they don't have memory, they don't have persistence. Whatever the input is given, it will just do the prediction. So single input, single output. Now, for example, if the input is text, the output is sentiment, whether the text is positive or negative. So here, no scope of context, no context accumulation. So that is traditional machine learning system, and hence we call it static inference. Static inference means, okay, whatever the knowledge the machine learning model has, based on that, it will give the input. Machine learning models, they cannot adapt, they cannot add new knowledge, they cannot learn during the runtime. All the learning happens during the training itself. And if on the other hand we look into the AI agents, they are dynamic in nature. So dynamic action. So machine learning systems, they do the inference, but AI agents, they perform the action, and they are dynamic in nature. So here the idea is that the loop which we already saw, uh, we have input. So AI agents, they take the input based on the, and AI agents, they have memory, and they accumulate the context, and they plan, they make an action plan, they execute it. So actions, they perform actions, and that actions will affect the future inputs, because the action will affect the environment. Because of that, the future inputs will get affected. So input will keep on evolving, and hence it is dynamic in nature. Because in machine learning, just we take a input and output, done, job done. But in AI agents, until the goal is achieved, it will keep on running this loop, and inputs will keep on evolving, because based on the current input, it will perform some actions, and that actions will further affect the future inputs. So inputs will keep on evolving. If we look at one example, like user complaint. So the initial input is the user complaint. Now the goal of the AI agent is to resolve that complaint. So for that, it will ask for more context. It will ask for clarification. And based on that, it will make an action plan. It will run some tools. It will execute that action plan. And then based on the outcomes, it will reflect. It will assess whether the goal is achieved. And it will keep on doing it. And if it feels like it is not able to reach the goal, then it will escalate. Accelerate means the complaint will now go to a human agent. So from AI agent, it will be transferred to human agent. So for AI agents, it is dynamic action, it is continuous learning and adaptation. And this is very important, adaptation. Here, the knowledge is evolving with time. There, the knowledge was fixed. But here, AI agents, they're reiterating their strategies, they're evolving, that their knowledge is evolving. Adaptation. Lack of planning in classical machine learning. So, for if we talk about traditional machine learning systems, they just do the static inference. They does not plan. They does not reason over sequences. They do not plan. They does not reason, and they does not evaluate consequences. So they're very static in nature. Wherein traditional machine learning system, they can just output, like they can just generate the output for the input. It cannot answer what should I do next. Like it's very passive in nature. But if you talk about, yeah, uh, because see, so it's very clear that traditional machine learning, there is a lack of planning, because planning, it requires goal awareness. And unfortunately for traditional machine learning system, it does not have any specific goal. It has an objective of minimizing the loss, but it does not have any goal to achieve. State tracking. In so planning requires state tracking. What is state tracking? Like, okay, based on the current state, the current scenario, I made an action plan, I performed some actions, and outcomes I assess. And based on that, I make a new plan or I revise the plan. So I have to uh, store the state, the previous outcomes somewhere, so that I can refer it in deciding, in revising the plan, in re-strategizing. So planning requires goal. There should be goal. There should be state tracking and outcome evaluation. So whatever action plan we made, we when we execute it, we have to evaluate the outcome. That is the reflect whether we are marching towards the goal or not. And if we are drifting away from the goal, it means there is a need to revise the plan. And we will revise the plan with an objective of reaching towards the goal. So outcome evaluation is something very important. And unfortunately, traditional machine learning, they have nothing to do with all this. So these like planning, it is outside the scope of classical machine learning. So classical machine learning, traditional machine learning systems, they have nothing to do with planning. They are very static in nature. Boundaries and brittleness of machine learning systems. Okay, so the idea is that, see, machine learning systems, they assume the real world to be very ideal, wherein it assumes that whatever knowledge the machine learning model has learned, that knowledge will be there forever. That knowledge will be applicable forever, but it does not happen. So machine learning systems assume an ideal world wherein it assumes that training data is approximately equal to deployment data. See, machine learning model, we train it in the lab and we make use of the training data. But unfortunately, training data is is a subset of reality. It's a sample of reality. Reality might have infinite possibilities. It might have so many scenarios which we cannot capture. So when we are training the model, we have to make assumptions. We have to take a chunk of the reality. And the problem with that is that it will miss many patterns. It will not learn many patterns. And during the production, if the input consists of those patterns which the machine learning model has never seen before, then it's gone. It will do the wrong prediction. So machine learning systems, they assume an ideal world wherein they assume that, okay, whatever training data we are using in the lab to train the model, the same data it will encounter, the similar kind of data it will encounter in the production when the machine learning model is live. But that is a wrong assumption. Machine learning systems, they assume stable task definitions and they assume predictable inputs. But unfortunately, the real world is very uncertain And because of this ideal scenario, machine learning systems assume consistent performance and reliable outputs. But the reality, the real world, the data drifts. The data might have noise. The data is incomplete. And the data drifts also, the patterns. The very good example of it is the COVID-19 pandemic. A complete change, like a very massive shift in the patterns. Because whatever the trend pre COVID-19, the trend post COVID-19 is completely different. Tasks, they are not stable, they evolve over time. And we might have those inputs which might contain patterns which the machine learning systems have never seen before. So edge cases explode. So and because of that, the actual result is that performance degrades, error cascades, manual intervention required. So this is like a very important discussion we are making. So machine learning systems, they are like they have boundaries and brittleness. Brittleness means like they are very fixed, they are rigid. They are good for one task. They are like highly specialized, but and they cannot adapt. So machine learning systems are very much powerful inside boundaries, but they are fragile outside those boundaries. Once you take the model outside the lab, in the lab you might get magical accuracy, because in the lab when you're training the model you might see, oh, such a good accuracy I'm getting. But the same model, when you deploy it in the production, you will start seeing the performance degrades, because the real world is very much different from the lab or the office where you are training the model. So that's the idea. Machine learning systems, they are powerful inside boundaries, but they are fragile outside them. How agents extend machine learning systems? Now this is very interesting. See, AI agents, they do not replace machine learning models, rather they extend it. They wrap, orchestrate, and extend them. So this is like a very interesting visualization. So we have a machine learning model. Now this machine learning model, like every model will have a specialization, a core capability, whether it can classify a particular kind of image, or it can like do some kind of a regression wherein it can predict some price or some recommendation or forecasting. So machine learning model is a core capability. Now agent, AI agent, it will not replace the machine learning model, but it will add more features to it. It will wrap, it will extend. So see, if I talk about machine learning model, what it can do is that it can play the role of perception. Like when we have to machine learning model, it can directly fetch in the input, and based on that it can do some sort of intelligence into it, like it can classify it, it can do some prediction. So in this complete architecture, wherein machine learning model plus AI agents, machine learning model plays the role of perception module, reasoning engine. To a certain level, machine learning model can play a role in reasoning and scoring function. So for AI agents, when we use machine learning models, what we can do is that with machine learning models, we can achieve the perception, we can achieve a sort of reasoning and scoring, that evaluation and all thing. And agent, they are very good in decision making, they are very good in planning, they have state, and they can execute actions. So the idea is that machine learning, it's good in answering questions, and AI agents, they are very good in deciding actions. So that's the idea. So this is a very powerful framework we are discussing, wherein agents, they make use of machine learning models for perception, reasoning, and scoring function. And agents, uh, like on their own, they are like very much capable of decision making, planning, memory, and execution. And this complete setup is like a very powerful framework which can answer questions also, and which can decide actions. planning plus execution layers on top of machine learning. Okay, so this we already saw, like got some idea. So the idea is that see in agent, if we talk about AI agents, we know that they have a perception layer, they have a planning layer, because this is the cycle we are discussing. They can execute actions, execution layer, and feedback layer is also there. And based on the feedback layer, it will do some adoption, uh, like some behavior adjustment, and this loop will go on forever. Now, we already saw in the previous slide, perception machine learning models can play a role, like vision models, classifiers, a sort of LLMs also can play a role in perception. So once we get the input, AI agents got the input, they did like from the perception layer, and the AI agent it is aware of the goal also to be achieved. Then it will make the plan. The planning layer, what it will do, it will that the task, the goal to be achieved, it will decompose it. It will make an action plan, and it will make a strategy to execute those actions. Then execution layer, what it will do, it will call the tools for the execution. It might call API also, and when it will execute, the environment will change. And feedback layer, it will assess the environment, it will observe the outcomes, it will detect errors, and based on that, the planning adjust behavior. So the revise planning, re-strategize, and once again, the changed environment, we will perceive the inputs and planning and execution. So the idea is very clear. Traditional machine learning systems, they are only good in perception, and with agentic AI, we can have planning plus execution layers on top of machine learning, and that is what we are discussing. So this layered approach transforms intelligence into agency. See, until now, traditional machine learning systems, they were good in answering like questions, but they were very passive in nature. Like machine learning systems, we can use for analysis. Now, with agents into the picture, the planning and execution layer and the feedback layer, now that analysis, it got converted into agency, wherein now we are acting on the analysis and we are adapting our strategy. That is very powerful. So real time adaptation. So traditional machine learning systems, they are very static in nature. During training time, whatever knowledge you fed, it only has that. It reacts the same way every time. It requires retraining to change behavior. To change the behavior, to add new knowledge, we have to retrain the model. So it's very static in nature, which we already saw. First, we train the model, machine learning model, we deploy it, and it will just give static responses. Now, if we want to evolve the model, we have to retrain it. And this cycle we have to keep on doing. Now, machine learning models, they are not at all resilient to errors. Let us suppose any API fails. The ML model cannot do anything. It will also stop working. On the other hand, agents are dynamic in nature. This we have been seeing. They adapt during execution. So they make a strategy, they execute that strategy, and they observe the outcomes. And based on the outcomes, they adjust the behavior, they revise the plan, they re-strategize. So they adapt during execution. The goal is to the main idea is to achieve the goal. They change plans mid task. They respond to failures. That's very powerful thing about agents. So the agents, they execute, they monitor, they adapt, and they keep on continuing. So they execute a strategy, they monitor the outcomes, and based on that, they adapt. Adapt means they revise the plan, they re-strategize, they adjust behaviors, and they keep on doing it until the goal is reached, the goal is achieved. So if API fails, for agent, it will retry, and once again it is not able to hit the API, it will switch source, or in the worst case, it will escalate, wherein it will request for a human intervention. So here the system is not failing, it is handling the errors. So the conclusion is that adaptation happens at runtime for agents, And the good thing is that no retraining time, no need for retraining and all that. So that makes it very powerful. Decision loops versus one shot prediction. So see, machine learning systems, they are linear process. Like input we give, the machine learning system will make some prediction and done. So it is like a one shot. So machine learning is like one shot prediction. One shot prediction means one input, one output, session is done. No, we are not at all considering the context. So machine learning is like a linear process. It is stateless operation, single shot stateless operation. But agentic systems, they are cyclic loop. We can also call it the decision loops. So it will keep on like watching the state, it will decide, it will act, it will observe, it will update the strategy, and it will keep on doing it until the goal is achieved. So this loop continues until goal is achieved, confidence is low, human intervention is needed. So the main idea is agents think in process, not outputs. So for agents, it is a cyclic loop. It's a total process until the goal is achieved, or if the agent is drifted away from the goal, human intervention is needed. Then this loop will stop, or when the goal is achieved, then this loop will stop. Otherwise, this loop will keep on running, running, running. But for machine learning systems, it's like a very one-shot prediction, stateless observation. So agents think in processes, not outputs. Why agents are not just LLM wrappers? So if we talk about large language models, so we know that large language model is the core component of an agent, because all the intelligence is there with the large language model only. Now large language model, it has the capability of generative AI. It can generate text. So large language model, it can only generate content. It can generate text. It can generate images. It can generate videos, audio, but it can only generate. Large language model, they don't have any goal, because whatever input you will give, it will just generate that. It will just generate a response. It does not have any goal. Large language model on its own does not have any persistence. They're stateless and they cannot act. They don't have any execution capability. So this is a very important discussion we are making. It's very important for you to realize the difference between LLM and agent, because most beginners, they might have a misconception that LLM is in itself an agent. No, large language model is very passive in nature, wherein large language model has got all the intelligence, no doubt in that, but it can only generate, it cannot act, it does not have any persistence, wherein it will not remember the interaction, and it does not have any goal. On the other hand, if you talk about agents, they are the autonomous system, they are goal driven. So agents, they make use of LLMs as reasoning components. They maintain goal, they execute actions, they track outcomes, and they operate over time. So the idea is that wrapping an LLM with tools does not create an agent. So if you wrap an LLM with tools, it will not be an agent. For a true AI agent, we should have goal. Goal is the most important thing. Adding decision logic, memory, and autonomy will create an agent. So the idea is that LLM, so we should have LLM is like the most important component of an agent. It is a reasoning component. And apart from that LLM, we should also have a goal. We should have some decision logic, state, memories plays a very important role, memory, and autonomy. Autonomy means uh, agent, there should be a framework wherein the agent on its own will decide the strategy to solve the problem, to reach the goal. So that autonomy is very important. Side by side comparison summary. So like if we just quickly summarize the differences. So traditional machine learning, the purpose is prediction, because it can only predict. And AI agents, the purpose is decision and action. So the AI agents, they will keep on making the plan, decide, and act until the goal is reached. The scope of traditional machine learning system is one shot, and for AI agents, it is continuous. For traditional machine learning systems, no memory. AI agents have got persistent. They can store the state. Traditional machine learning systems, no planning at all. AI agents, planning is the most like very important. They plan. For traditional machine learning systems, adaptation means if we want to evolve the model, add new knowledge, then offline retraining we have to do. And AI agents, they can do the real time adaptation. They can learn on the fly. That's a very powerful thing about AI agents. For traditional machine learning systems, there is no concept of autonomy. And for AI agents, autonomy is the core feature, wherein AI agents will decide the plan. They will make the plan, they will make the strategy, they will execute, they will decide which tools to call, all that. And then they will reflect the outcomes and they will re strategize, they will adapt. They'll keep on doing it until the goal is achieved. So, finally, we completed this lecture. So, we saw that traditional machine learning systems are components, because traditional machine learning systems, they are like individual components, they are highly specialized, they can perform a certain action, and they're very passive in nature. But AI agents, their system. Machine learning gives us intelligence, and AI agents, they give us operational intelligence, wherein we will like execute something, like we will achieve a goal, like operational intelligence we can achieve via AI agents. And the future is the present, and the future is the agentic AI. And very interesting thing is that you cannot ignore machine learning, because we saw that machine learning can play a very important role inside the agentic framework, wherein we saw that in perception, machine learning models play a role. So machine learning has got its own benefits, and AI agents have got its own benefit, but the difference should be very clear. And that was the purpose of this lecture. And I hope you got a very good understanding of the concepts which we discussed in this lecture. So do subscribe to our YouTube channel, ScaleUp University, for more such interesting lectures and courses. Thanks for watching. Thanks for your time.